Hello, it's PF, here's the tutor again. Welcome to this video. Physics Science 2019, Paper 1, Question B5. It says, the human audible frequency range is 20 Hz to 20,000 Hz. Taking the speed of sound in air to be 330 meters per second, what is the upper limit of the human audible frequency in kilohertz? So for you, so we have the lower limit. All right, the lower limit is this 20 Hz. All right, and the upper limit is 20,000 watt Hz. Now they want this in kilohertz. We know that 1 kilohertz is equal to 1,000 watt Hz. So this will just be 20 kilowatt Hz. We're just converting this, which is the upper limit, into kilohertz, knowing that 1 kilohertz is equal to 1,000. So we are just replacing this 1,000 with kilohertz. That's all. What is the wavelength or the upper limit of the audible frequency? Now we know that speed of sound is given by frequency times what? Wavelength. Speed like we have been given 330 meters per second is equal to frequency. We have frequency. Frequency we have. They're looking at the lower limit. Lower limit. So the lower limit is 20 Hz times u. So we are looking for this, which is the lambda, the wavelength. That's a symbol for wavelength. Then we have to divide both sides by 20 Hz and this side by 20 watt Hz. So we cancel that, so it remains what? Lambda is equal to, so 330, so 330 divided by 20, you're getting 16.5 meters. So here the answer is 16.5 watt meters. Question B says, figure B5.1 is a diagram of a wave traveling through air, which labeled this distance represent one wavelength. Now, what is a wavelength? A wavelength is the distance between two successive crests or two successive troughs. So which letter here represents one wavelength? Now here is a thing which you must know, right? A wavelength is from here up to the last one there. That is a wavelength. Why? Because you have this, and this making up one frequency. So that's W. The amplitude of a wave. The amplitude is the maximum displacement of the wave from each rest position. So therefore the amplitude is this. This is the line you are seeing here is the rest position because it's 0 there. So that's a rest position. So from there up to where it is. If we had something like that, we could also put X. B6 says, figure B6.1 is a diagram showing the appearance of the coin immersed in water when viewed from above. State Snell's law. What is Snell's law? State it. So it says Snell's law states that the ratio of sine of angle of refraction to the angle of sine incident, angle of incident is a constant. Sorry. So constant. Okay. In other words, we are saying sine R over sine I. Oh, sorry. It's supposed to be sine I over sine R. So here it's supposed to be the sine of angle of incident here incidence, then here supposed to be refraction. It's a constant, so it's supposed to be like that, is equal to n, something like that. What happens to the rays of light at the surface of water above? What happens to the rays of light, all right, at the surface? See, so there. What happens to the rays of light at the surface of water in this figure here? Because this is water. What happens to the rays of light here? What happens to the rays of light is that since the rays of light are here, right? So this is water, are here. This is water. Then the rays of light are somewhere coming like that, down like that. So as they are coming towards the other medium, this is air, this is water. So as they are coming like that, what happens? They refract. Calculate the refractive index of water. The refractive index of water is equal to, let's look at this, is equal to the real depth versus the apparent depth. So this is the real depth here, this is the apparent depth. So the real depth divided by apparent depth. Sorry. So depth is equal to, real we have 15 centimeters divided by, we have 11.28 centimeters. So we need to divide 15 divided by 11.28. We have 1.33. 1.33. It has got no units, it's a ratio. So thank you so much for watching. I'll see you in the next video.